Have you ever wondered where all the antimatter went? In the beginning, there was the Big Bang, a colossal explosion from a point of singularity that birthed our universe. This cosmic event, according to our understanding of physics, should have created equal amounts of matter and antimatter. Picture this. For every particle of matter, there should be a twin particle of antimatter. Antimatter is not some science fiction trope. It is as real as the matter we interact with daily. It's like the mirror image of matter, with opposite charge but identical mass. When matter and antimatter meet, they annihilate each other, releasing energy. But here's the cosmic quandary. When we look around, we don't see any antimatter. Our universe, as far as we can observe, is overwhelmingly made of matter. Our galaxies, stars, planets, and even we ourselves are all matter. So if the Big Bang created equal amounts of matter and antimatter, why does our universe appear to be made of matter only? The mystery of missing antimatter is one of the greatest puzzles in science. For decades, the brightest minds have been trying to crack this enigma. You see, in the wake of the Big Bang, matter and antimatter should have been created in equal amounts. But here's the rub. When matter and antimatter meet, they annihilate each other, leaving nothing but energy behind. So if the Big Bang produced equal amounts of both, why is our universe made almost entirely of matter? One theory suggests a slight asymmetry in the laws of physics. This twist might have tipped the scales, causing a minuscule surplus of matter over antimatter. It's this tiny excess that could have survived the mutual annihilation, forming the stars, planets, and galaxies we see today. But this theory, while plausible, is still unproven. The mystery of the missing antimatter remains unsolved. So, the quest to understand our universe continues, with antimatter at the heart of the enigma. Our quest for understanding doesn't stop at theories. Scientists are actively searching for signs of antimatter. To do this, they're using some of the most advanced technology available to us: high-energy particle accelerators and space telescopes. These accelerators smash particles together at nearly the speed of light, creating extreme conditions where we might expect to find antimatter. In these fleeting moments, researchers have indeed managed to create antimatter in the lab, yet it's proving elusive in the vastness of the universe. Space telescopes, on the other hand, offer a different approach. They scour the cosmos, looking for the distinctive energy signature that antimatter might leave behind. Despite these concerted efforts, our universe seems to be playing an elaborate game of hide and seek, with antimatter being the ultimate prize. So, while we've made strides in understanding the nature of antimatter and even producing it in controlled environments, its cosmic absence remains a mystery. So, the hunt for antimatter continues. What would it mean if we found antimatter in the universe? Unearthing the existence of antimatter would be tantamount to flipping our comprehension of the cosmos on its head. It would present an entirely new chapter in our understanding of the universe, pushing us to reevaluate the fundamental laws of physics. But the implications span beyond the theoretical. Antimatter holds the promise of an energy source far more potent than anything we currently possess. Imagine a future where a few grams of antimatter could power entire cities for years, a world no longer reliant on fossil fuels, a world where energy is clean, abundant, and limitless. Yet, this powerful potential also carries risks. Misuse antimatter could lead to devastating destruction. Hence, the discovery of antimatter would also usher in a new era of responsibility. The search for antimatter isn't just about solving a mystery, it's about understanding the fundamental nature of our universe.